started the second video today, and now let's get back our presentation here. Okay, so just a quick summary in perhaps easier words. We talked about the robustness function of the InfoGap method, and here is the robustness function, which relates the maximum level of uncertainty that we can tolerate to the benefit, and in particular to the benefit, critical benefit. So we have to identify in our problem the minimum requirement. Okay, so we made the example of water for irrigation. What is the minimum benefit that we want to get from the crop? And then depending on this minimum benefit, which could be in this figure that you see on the screen, could be 15, we estimate a max tolerable uncertainty, which is 1. Okay, and this tolerable uncertainty H, according to our uncertainty model, has been estimated as you see here. It's H is the true X minus the best estimate of X divided by our estimate of uncertainty S. And then we understand what is the max level of H that we can tolerate, the max uncertainty. And of course, I am happy if I can tolerate a large amount of uncertainty. So bigger is better in this case, because I think, okay, even if my model is not a good one, I can reach the minimum requirement in an easy way, because I can tolerate a lot of uncertainty. I can tolerate if the model is not very good, in both giving to me the best estimate and the uncertainty associated to the prediction. Okay, good. But now we have to identify also the opportunities, because here we are just fixing a minimum benefit, and we are not considering what could be a windfall. And we said that a distinguishing feature of this method is precisely that we also look for a windfall. And if we get a windfall, it is an unexpected benefit, which means that unexpected means that it's better than my best estimate, because the model gives to me a best estimate. A best estimate which I identified with the tilde. And but if I look for an opportunity, the opportunity means that is unexpected. So it's something that the model is not predicting. So it is something that goes beyond, is much better than the benefit given by the best estimate. Okay. And in order to get it, I need uncertainty as well, because in order to get something unexpected, it means that it goes beyond my prediction. It means that my prediction was wrong, okay? So I also need uncertainty, and this is the distinguishing feature of InfoGap. InfoGap recognizes that uncertainty may bring an unexpected benefit. And in this case, the objective is to estimate what is the uncertainty that I need to get this windfall, this unexpected benefit. So I want to consider whether my decision in the presence of uncertainty may bring something really unexpected. And in this case, if you think of it, it's much better if I have a low uncertainty, giving to me the possibility of getting an unexpected benefit, because I mean, I have a prediction. If I want to get more than this prediction, I need uncertainty. We recognize this. But if I see that I need a lot of uncertainty, I need to really get something that is far from my best prediction to get a windfall, I'm not happy. I am more happy if I see that with a small, maybe a small amount of more water, a small additional amount of water, I can get an unexpected windfall. This is what makes me happy. Like, okay, my model gives to me this prediction, but with a tiny increase of water for irrigation, I may get this unexpected windfall. And if I only need a small uncertainty in the prediction, I am happier than the situation where I see, okay, in the future I have a prediction of 10 millions of water. In order to get an expected windfall, I need twice that. So one thinks, okay, my prediction is wrong, but it's difficult that is so wrong. Instead, if I see that the windfall is obtained with 1% more of water, then I am more happy, because it means that even if the model is almost precise, but with a very tiny uncertainty, I can get the windfall. So you understand that when I look at the opportunities, I am happier if the uncertainty for giving to me the opportunity is smaller. So in this case, smaller is better. Okay, so let's try to look at. So we need a performance aspiration in this case. So we need in the previous situation, we needed to fix a critical value of the benefit, which is lower than the best estimate, because I optimize my decision for the best estimate. So I need to fix a critical value of the benefit, which is lower than the best estimate, in order to make my decision sustainable. When I look at the opportunity, I have to fix an ambition. So what is the windfall? It is a benefit that is larger than the best benefit, the benefit corresponding to the best prediction. So I need to set the ambition, a performance aspiration, and then let's call it BW, where BW is just 1 second. Here there is let me see. Here there is the slide. You see that there is a visualization problem. So this BW is larger than the benefit corresponding to the best prediction, as I said. Okay, so let me just check if I can resolve this problem immediately in the slide. Just 1 second. It looks like I can't remove this. Okay, grazie. Yeah, probably. Just 1 second, give me 1 second, because I need to extract it. Anyway, it's too late. Let me just try to clarify. So BW is larger than, of course, is larger than the critical benefit, and it's also larger than the benefit which corresponds to the best prediction. In fact, you see in the first sentence, it is correct. The desire for an outcome that is better than B tilde. B tilde is the benefit corresponding to the best prediction. And sorry, the visualization is not clear. I will check. I will check for the download. Give me. I will change the PowerPoint in the website. Give me a couple of hours, okay? It is good. Okay, it is good. Okay, perfect. Thank you. So I apologize. Okay, yeah, okay. Because I think this is a problem that I get when that's fine. So in the website is good. Perfect. So sorry for that. Okay, so the question asked by the windfaller, the person looking for the windfall, is what is the lowest horizon of uncertainty and which windfall is possible, even if it's not necessarily given. Okay, so this is the question. Okay, good. Now, this is the opportuneness function. This is the mathematical formulation. And if we translate it in graphical terms, it is the red curve. The red curve, you see that it goes beyond the benefit corresponding to the best prediction. It goes beyond that because we are looking for something more. The windfall is more than what we are expecting, is more than the benefit given by the best prediction. And as I go further with the benefit, as I look for more money, it gives to me what is the minimum level of uncertainty required. Of course, I would be happier if this red curve was less steep than that. If it was a red curve like moving almost horizontally, I would be happier because I am happy with the minimum level of uncertainty. Mathematically speaking, here you see I am looking for the minimum uncertainty. It's a dual expression with respect to the one that I saw before for the robustness function. Here, my target is to get a benefit that is larger or equal than my windfall BW. I'm looking for the minimum uncertainty in order to get this unexpected windfall. So you see that this figure, once I fix here the value of critical B, which may be 15, as I said, and I fix here a value for my windfall, which may be 30, I get an estimate of the max uncertainty that I can tolerate for a benefit of 15. It's about 1. And I get an estimate of the minimum uncertainty that I require in order to get 30, which is 1.2. And then you can make your decision by evaluating the risk that you have not to reach the critical value and the probability that you may have to get the windfall. But the nice feature of this method is that through this robustness and opportuneness functions, you can evaluate also the opportunities given by climate change. Keep in mind that when you speak about opportunity given by climate change, it is a sensitive issue. It is a sensitive topic because, if you think of communication and the sensitivity of the policymakers to climate change, if you highlight, if you admit the possibility that there might be opportunities related to climate change, the effectiveness of the communication may be undermined. So this is why it's sensitive. But as engineers and policymakers in general, we need also to be aware of the reality of facts, and also we have the duty, like when we manage the pandemics, to try to transform the crisis into an opportunity, because this is the way we make progresses. We make progresses if we are able to learn by mistakes and to also find opportunities. And the crisis indeed may present opportunities. The fact that climate change may be an opportunity, at least for some regions of the world, is clear. So if you think of regions where they have already a lot of water and maybe that they are too cold for promoting agriculture, they have water for agriculture, but they don't have the temperature, then an increase of temperature may allow these regions to become more prosperous. Of course, instead, if you look at arid regions, it's not an opportunity. So the opportunity and also the impact of climate change depends, as we said many times, on the local context. But this method gives this possibility to also evaluate the opportunities. Mathematically speaking, is not easy, and the notation may be something that, but it should be, everything should be correct. But as I said, if you think that something is not clear or missing, just let me know, we can improve it together. Let me just check. These considerations, I think they are obvious because they are not obvious, but I already made them, okay? So basically, I think that what we can conclude by saying that this method is particularly useful if you, like in our case, if you don't have a precise estimate of uncertainty. In some cases, you may have indeed an estimate of uncertainty that is reliable. For instance, even in this context, we talked about climate models and we talked also cascade of models. So we talked about also hydrological models. Uncertainty of hydrological models is lower than uncertainty of climate models. And it also uncertainty estimation for hydrological models can rely on extensive validation, which means model testing with respect to real observations. For climate models, this is more difficult. It's more difficult because for certain variables, we don't have long series. And also certain variables are affected by larger variability in climate, and therefore they are more difficult to test. So remaining in the context of climate models, uncertainty assessment for future temperature is more reliable than uncertainty assessment for future rainfall, because rainfall is a variable that is more difficult to predict. But if you start from a good prediction of rainfall, then the prediction of river flow and water resources in general is estimation of uncertainty is more reliable than estimation of rainfall. So I'm doing these considerations because what I want to say is when you have a reliable estimate of uncertainty, I think that you may adopt also different approaches, because if you have outcomes that are very unlikely, then they shouldn't be probably considered. But if you don't have a clear idea of uncertainty, this type of approach, which considers the possibility of what may happen and reverts the logic, so doesn't rely on the estimation of uncertainty, but relies on the estimation of what is your ambition, your aspiration, and the estimation of what is sustainable and what is not, and then estimate the uncertainty that you can tolerate. I think this is much better. And then the good question you may have is, how can I recognize when an estimate of uncertainty is reliable or not? This is a question that is very difficult, and you may read the literature, or you may get advice from experienced users, experienced researchers. It is not easy. So what I told you that hydrological models are, in terms of uncertainty, estimation of uncertainty for hydrological models is more reliable than estimation of uncertainty for climate models. This is not easy to be found, such a conclusion. You need to read a lot of literature. But in any case, you can rely also on consultation with experts. And it is indeed, when you talk about uncertainty, it's not easy. On the other hand, it's very exciting because, as you see, uncertainty may deliver also windfalls. And this is something that we need to properly consider. Okay, and then there is another method which is much easier, so I don't want to, but next Monday, I still have a final hour with some mathematics to introduce another one. Questions? Yeah, please.
Just to be clear, the critical value of X is something that we obtain from fixed and defined by the project critical value of the benefit.
Yes, 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 yes. Typically, when you deal with a design project, there is a target in terms of benefit. And the benefit is not only economic, maybe also benefit in terms of environmental impact. And then you need to scale back to a decision variable, in this case X, which leads to this benefit. This is the generic structure of the problem. In some of the cases, you may have also the benefit directly defined in terms of X. Like, for instance, I need an environmental flow of at least 1 cubic meters per second. And then you work, the decision variable is directly the river flow in this case. But usually when you talk about irrigation, in terms of irrigation, usually people say, I need to irrigate at least 10 hectares of land. And therefore, and then you scale back to the X. Okay, other questions? Good, thank you very much. And so see you next Monday. And then once again, for those of you who joined later, we conclude next Thursday, 25th, not the next one. On Thursday, 18, we don't have any lecture, like in the calendar on my website. And we conclude Thursday, 25th, with 1 hour of lecturing and 1 hour in the lab and a coffee at the bar, okay? Good, thank you.
Thank you. Goodbye.
Bye-bye.